In the last section, when we discussed rates of change, we were talking about the behavior of intervals as the intervals got smaller and smaller and approached a particular value. So what we're going to do in this particular lecture is we are going to talk about the concept of a limit. And the concept of a limit basically goes after what is the behavior of a function, meaning the y values, as you approach a particular value of x. So to get started, let's go ahead and look at limits. Again, the idea of a limit is we can look at a graph. One of the approaches that we'll use. We'll look at a graphical and numerical, which we've already talked about in our previous section, and we'll also look at an algebraic approach. But we're trying to look to see what the behavior of a function is when I approach a particular value, as I get closer and closer to a particular value. Now, it doesn't matter whether the function is defined at a particular point. We can still talk about the behavior of the graph or the function around a particular point. Basically, what the upshot is, what do the y values do when x gets close to a particular constant c? So I think to start with this, the best thing to do is to go ahead and look at an example. For this particular example, we are going to be talking about the function f of x equals sine of x over x. Now the graph for this isn't real obvious. We'll use Maple to plot this for us in just a minute. But what I want to determine is what is the function doing, or what is the behavior of the function near x equals 0. So notationally, what we're trying to determine is the limit as x approaches 0, this is LIM for limit, as x approaches 0 of sine x over x. Now what we do ideally is we plug in directly to see what's happening with this function at 0. So if we plug directly in, and this should always be our first strategy when we're working with limits, I get the sine of 0 over 0. This is 0 radians, of course. The sine of 0 radians is 0, and I get 0 divided by 0. There's a lot of zeros running around here. Now, what I would like to know is 0 over 0 undefined. Usually if there's a 0 in the denominator, we say the fraction is undefined. But we need to think about this a little bit differently. We're talking about the behavior of a function near a particular point. 0 over 0 is not undefined, it's indeterminate, meaning I'm not sure what's going on. So this is indeterminate. Now when we're using limits and we take a value and plug it in and we get 0 over 0 or indeterminate, this has an implication that we need to do more work. So this is what you should always think. Indeterminate, do more work. That'll kind of set you on the right path to try and figure out what's going on with this particular limit. And again, we're talking about what is the y value basically getting close to, if close to anything, as x approaches 0. So I would like to look at this graphically. Now the best way to start with this is to go ahead and open up Maple if you don't already have it open, and let's try and graph this function. So when we open Maple, first of all, let's go ahead and have a look at the function. Sine of x divided by x. And remember, always put parentheses around the arguments of your trig function, and every command line in Maple should end with a semicolon. This is the function that I'm looking for. So I'm going to right click and choose plots. I could also use a plot command and look at a 2D plot, and there's a nice little graph of sine x over x. I think I want to change this just a little bit because I want to get an idea of what this point is. It looks like it's 1, but I want to make sure of that. So instead of just going to 1 here, let's go to 1.2. Yep, it is going right toward 1. Now this is a nice little graph, so I'm going to copy it and paste it into my document so I can do some writing on it to try and talk about the behavior of this graph. Okay, so let's go ahead and have an idea about what's happening here. Well, first of all, this graph has a little bit of a problem. At 0, this fraction right here has a 0 in the denominator, so this should have a hole here. So this should be a hollow point on the graph. And again, Maple doesn't catch that, so you need to catch that. It's a hollow point on the graph. Now what I want to do is I want to talk about what's happening with this graph as I get closer and closer to 0. Now the way we work with limits is I talk about the limit from the right and I talk about the limit from the left. So notationally, I have the limit as x approaches 0 from the right, the little plus sign says right, of my function sine x over x. Now if I watch this behavior, as I get closer and closer to x equals 0, my y value is getting closer and closer to 1. Now it never reaches 1, and that's okay. It approaches 1. And a functional value and a limiting value don't have to be the same thing. A lot of times I can just talk about the behavior near an undefined point. Over here on the left I have the limit as x approaches 0 from the left of sine x over x, and I can see from the left my y values also get closer and closer to 1. So the limit from the left and the limit from the right agree. That gives me an idea of what the overall limit is. So the way I usually think about this is I say, okay, the limit as x approaches 0 from the right is equal to the limit as x approaches 0 from the left, and they both agree at 1. Therefore, and the three dots in the shape of a triangle mean therefore, the overall limit at 0 of this function of sine x over x equals 1. So the limit from the right and the limit from the left have to agree in order for this to happen. Now that's how we can look at evaluating a limit graphically. We could also look at evaluating a limit numerically, and this is where we're going to be producing a bit of a table. So let's go ahead and look at the same example, f of x equals sine x over x. And here I want to determine the limit as x approaches 0 again of sine x over x, but I want to do this numerically. Graphically we already have an answer that seems to make perfect sense. Let's go ahead and look at this numerically. Well, what we'll do is we'll produce a table kind of like we did in our last lecture. And in this table we will approach 0. We'll get very, very close to 0, but we can't ever actually reach 0. We can't plug 0 in, because when I do, I get an indeterminate form. So I'm choosing values that approach or get very, very close to 0 from either side, and I'm looking at the behavior of the function. Now I don't want to go start over here at negative 100 and approach 0 in that direction. I would want to approach 0 very, very close. And I'm approaching from the left, so I'm approaching from the negative direction. Over here I'm going to approach from the right. Now when we plug these values into our calculator, make sure that you remember we are working in radians. So now this ratio down here would be sine of x over x. So I take this value of x and I plug it in to my function. So for this example, this would be the sine of a negative 0.01 divided by negative 0.01. And remember, you are in radians. Please double check that you're in radians. Now if we fill in this table, here I'd get 0.49s, an 8, and a 3. In this particular part of the table, something very similar, I get 6 9s, an 8, and a 3. And I think you can kind of see the pattern here. And then there's an 8 at the end here. Now from this direction, I kind of have the same pattern occurring. This one's going to be a little bit different. But we can see the behavior here is as I approach 0 from the left, this is getting closer and closer to 1. As I approach 0 from the right, it's getting closer and closer to 1 as well. So what we have here is the limit from the right agreeing with the limit from the left. So here I have the limit as x approaches 0 from the left of sine x over x equals 1. Over here I have the limit as x approaches 0 from the right of sine x over x is equal to 1 as well. Because the limit from the right and the limit from the left agree, this implies that the overall limit as x approaches 0 of sine x over x equals 1. And this is very good news because our numerical approach matches what the graphical approach said. Now, if the numerical and graphical didn't agree, we would know we'd have trouble and we'd have one of these were wrong, one or both of these are wrong. Let's go ahead and look at another example. For this example, I'm looking at the limit as x approaches 4 of negative 3x plus 10. This is a nice line. This is a nice graph to work with. I don't think we need maple for this one. So the first thing we always do when we're working with a limit is I plug directly in and see what happens. So I have negative 3 times 4 plus 10. Negative 12 plus 10 is negative 2. So I get a finite value. I don't get anything like 0 over 0 or 6 over 0. This is a nice finite value, so this is actually my limit. But I can also look at this graphically to see if the graphical approach verifies just the plug and chug approach. And it's going to be a little bit difficult because I don't have a nice proper scale here, but we should be able to ballpark it pretty close. So my y-intercept here is 10. My x-intercept, if I set this equal to 0, is equal to 10 thirds, which is 3 1/3. And I want to know what's happening at 4. So here's my graph of my line. Okay, and I would like to know what's happening here at 4. So as I approach from the right and I approach from the left, it looks like it's agreeing for my limiting value to be right out over here. And again, my graph doesn't show this accurately at all, but it seems that negative 2 would be reasonable. So the graphical approach supports plugging directly in. Let's go ahead and look at another example. For this example, I would like to determine the limit as x approaches 2 of 2x plus 3 over x minus 2. Okay, we've got trouble here, don't we? So if I look at this, what ends up happening is I see when I plug directly in, I'd have 2 times 2 is 4, plus 3 is 7, and of course 2 minus 2 is 0. Now 7 over 0 is not indeterminate. 7 over 0 is undefined. This implies the limit does not exist. So my answer here is D and E. Now D and E stands for does not exist, just to clarify, and we'll use D and E all the time, but you should know what it stands for. It does not exist. But the question is this: we know the limit doesn't exist, but why doesn't it exist? And one thing that we can do is we can look at this graphically. So let's go ahead and pop into Maple real quick, and let's go ahead and graph this function. So let's graph in our numerator 2x plus 3, and remember we need 2 times x plus 3 divided by x minus 2. Don't forget the semicolon. We'll right click, plot this, and this is an awful picture of this graph. I think what we have here, if we focus in right here, this is where the best part of this graph is occurring, right in here. So we need to zoom this in right around this area, and we also need to figure out what's going on with this. Well, what this is this is x equal 2. This is our asymptotic line. So what it's trying to do is it's trying to head up toward positive infinity. So here it is at 20,000 heading off toward positive infinity. So if you click on this, this little toolbar should pop up, and we can fix this. And remember, I'm wanting to focus right around here at 2, so I'm going to go 0 to 4. Okay, and let's hit apply. Yeah, that looks a little bit better. Now in the vertical direction, I don't think we need to go up to 20,000. That doesn't seem reasonable. So let's go ahead and let's say negative 10 to positive 10. And this might not be a good scale to look after, but it's a terrible scale to look after. We need to go higher than this. Let's go negative 30 to positive 30. We zoomed in a little too much vertically. Yeah, this gives us a good look and see what's happening here. Now again, I have to understand that this shouldn't be there. This is not a straight line. This is actually a vertical asymptote. And remember, when we do our plots, we can use the command discont equals true to get rid of that. I'm just going to copy it in as is, as long as we understand that that is not a vertical line. That is a vertical asymptote. It's a dotted line. And then I can start talking about the behavior of this function. So first note, this is actually a vertical asymptote. Now here, the limit as x approaches 2 from the right of 2x plus 3 over x minus 2 equals positive infinity. This graph is heading up toward positive infinity. Over here, the limit as x approaches 2 from the left of 2x plus 3 over x minus 2 is equal to negative infinity. This thing is heading off toward negative infinity. Well, I have a little bit of a problem here. The limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Therefore, the limit as x approaches 2 overall does not exist. D and E does not exist. Because remember, from the left we went toward negative infinity. Negative infinity does not equal positive infinity. So this is a good look at a graph where the limit doesn't exist. However, it doesn't exist because of a particular reason. So it's never enough just to say D and E. I need to know why it's D and E. So we have to do a little bit further investigation. Let's go ahead and look at another example. There's some basic graphs that would behoove you to know about, and one of them is 1 over x squared. So let's go ahead and look at the limit as x approaches 0 of 1 over x squared. Well, if we plug directly in, I get 1 over 0, which is undefined. Undefined implies the limit does not exist. D and E does not exist. But I want to know, why doesn't the limit not exist? So let's go ahead and look at a quick graph. The graph of 1 over x squared looks something like this. And you can grab Maple and plot this, but knowing 1 over x squared is a nice thing to know. So if we look at this, the limit as x approaches 0 from the left, we can see is heading up here toward positive infinity. The limit as x approaches 0 from the right is heading up toward positive infinity as well. These agree. Therefore, the overall limit agrees at infinity. But then we need to think about what the meaning of that is. This is saying the limit is infinite, which is no limit at all. So this implies the limit does not exist either. Now notice for here, my limits from the right and the left agreed, but the overall limit didn't exist because they were agreeing at an infinite value. Up in my other graph, the limit didn't exist because the limit from the right and the limit from the left were different. So again, knowing some basic graphs will be beneficial. Knowing more complicated graphs, of course, will be more difficult. Let's go ahead and look at another example. For this example, I'd like to look at the limit as x approaches negative 3 of 2x squared minus 18 all over x plus 3. Now if we plug directly in, I get 0 over 0, which is indeterminate. And as soon as you see the word indeterminate, you need to think do more work. Now we have D and E, which stands for does not exist. And we have DMW now, which stands for do more work. So DMW is not a standard notation that you'll see in any math class. That's kind of my abbreviation for do more work. What you need to remember here is the D and E does not exist. So, do more work. Does the limit exist or not? I need to figure that out. Well, what we're going to do here is we are going to look at this from the algebraic approach. Now, from the algebraic approach, we will do things like factor, simplify, rationalize. These are all different techniques, and there's more than this, but these are the most common ones that we can use here. Well, if we look at this particular limit that we're trying to work on, what ends up happening is I look at this and I think, well, I can't really rationalize it. I could simplify it by factoring, so let's go ahead and factor out here. And as soon as we see that difference of perfect squares in the numerator, that tells me right away that I'm going to have something that will cancel. X squared minus 9 is the difference of perfect squares, which factors into x plus 3, x minus 3. And I can see right away here then the x plus 3's cancel. And this just boils down to the limit as x approaches negative 3 of 2 times the quantity x minus 3. Well, if I plug a negative 3 in there, I get negative 3 minus 3 is negative 6 times 2 is negative 12. That's my answer. So the algebraic approach is probably a little bit more common because we're used to manipulating expressions algebraically, rationalizing denominators, rewriting, simplifying, etc. So the algebraic approach is really nice here. If we wanted to look at this graphically, what I would get here when I graph this particular function is a straight line with a y-intercept at negative 6 and a slope of 2. Now in Maple it would not give us the hollow point as undefined at negative 3, but we understand it should be there because the original fraction was undefined at negative 3. Now for this last example, instead of being given a limit and asked to find a graph, we are going to be given a graph and asked to find what some of the limiting values are. So let's go ahead and punch in a nice graph. This is going to be a piecewise function and determine some limit. Okay, so here's our graph. Now this graph is defined differently over different regions of x or different parts of our domain. For here it's linear, here it's curvilinear, linear, and again a nice parabolic shape. The first thing I would like to look at is the limit as x approaches 4 of this function f of x. Well, in order to determine what this is, what I need to do is I need to break this up into a couple different parts. I need to look at the limit as x approaches 4 from the left, and I need to look at the limit as x approaches 4 from the right. Well, as we approach 4 from the left, here's 4. As we approach 4 from the left, we can see that my y values are getting closer and closer to 3. Now they don't actually equal 3 because I have a hollow point there, but a function does not need to be defined at a point in order for the limit to exist. Now here, as I approach 4 from the right, my y values are also approaching 3. Whoops. Now these are equal. Therefore, the overall limit as x approaches 4 of f of x is equal to 3. So this is an interesting characteristic about a graph. The function does not need to be defined in order for a limit to exist. Okay, I'm going to scoot these down just because I want to have the graph right by us when we answer these questions. Okay, the next one I want to do is I want to look at the limit as x approaches 2 of this function. Okay, well, if we want to find a limit, we have to approach 2 from the left, and we have to approach 2 from the right. Okay, as we approach 2 from the left, we can see my limiting value is 1. As we approach 2 from the right, we can see my limiting value is 1. And these agree. These are equal. Therefore, the overall limit as x approaches 2 is equal to 1. Now these are two very different problems that we have here. If you notice, my function is undefined at 4. There's a hollow point on my graph, but the limit existed. Over here, the function is defined at 2, but I still have a limit that exists. So again, a function does not need to be defined at a point in order for the limit to exist at that point, and that's our important takeaway from this. Okay, let's go ahead and make a little bit more room, and we'll look at another one. C. For part C here, I would like to look at the limit as x approaches 3. So the limit as x approaches 3 of f of x. And remember, this entire graph up here is f of x. So in order to figure out what's going on here, we're going to look at the limit as x approaches 3 from the left, the limit as x approaches 3 from the right, and compare them. So here's 3. As we approach from the right and from the left, we can look at these and compare them and see, here, let me see, I think we're supposed to be right out here at 2, that the limiting value is equal to 2. Now if you think it's more like 2 1/4, that's fine. That's not a big deal. The point is to understand it's whatever the y value is, and it's very, very close to 2. So I'm going to say that both of these are equal to 2. Now if you think they're 2 1/4, that's fine. Then your limiting value would be 2 1/4. It's whatever the y value is. Now because these are equal, therefore, the 3 dots mean therefore, the overall limit as x approaches 3 of my function equals 2. Now there's one more that I want to look at. This one's going to be pretty different. We're going to take the limit as x approaches 0. This would be d. So we're going to look at the limit as x approaches 0 of our function. Same thing, you take the limit from the left, limit from the right, and we compare them. Well, here's 0. As we approach from the left, my y value is approaching 0. As we approach from the right, my y value is approaching 4. Now remember, it doesn't have to equal 4, it's approaching 4. These are not equal, therefore the limit as x approaches 0 of f of x does not exist, because the limit from the right does not equal the limit from the left. Now again, The big takeaway point here is a function does not need to be defined at a point in order for the limit to exist at that point. So let's remind ourselves that one more time, and this is definitely a nice little quiz question. A function does not need to be defined at a point, meaning I can have a hollow point on a graph and still have a limit at that point. Okay, so again, it's how the function is approaching or getting closer and closer to a particular value. Now that we've talked about these ideas of limits, we're going to look at limits when we combine things into sums, products, difference, and quotient values. So all the laws that we're about to look at are used for computing limits of functions that are either constructed as sums, multiples, meaning they're multiplied together, products or quotients of other functions. Now all these basic limit laws that I'm about to work with assume that the overall limit exists. If the limit DNE does not exist, then these rules don't necessarily apply. So again, all of these assumptions are the limit of both of the functions f of x and g of x must exist, and this is really important. The first thing that we're going to look at is called the sum law. Now we've actually done the sum law, so let's go ahead and have a look. The way we would say the sum law is the limit of a sum is the sum of the limits. And we actually already did this up above when we had like the limit, I believe, of like negative 2x plus 3, where we had that line. What that means is, and this of course is sum or difference, if I have the limit of a sum or difference, I can take the limit of each piece and then combine them either by addition or subtraction to get the overall limit. So for instance, if I was looking at the limit as x approaches 2 of x squared plus x, I could just take the limit of each individual piece. And we can see that both of these pieces, the limit exists, therefore the overall limit is 6 in this case. Now I don't expect that when you're showing your work that you're going to rewrite them like this. I expect that you're going to plug directly in. If you get a nice finite value, you'll be done. The next one I'm going to look at is called the constant multiple law. And this is basically when we have a constant times a function, and what that says is you can actually factor that coefficient or that constant out front. So for this example, I'm looking at the limit as x approaches c of some constant times a function. And again, as the constant multiple law says, you can pull that constant out front and then take the limit of the remaining function. So for instance, and this is such a simple case, the limit as x approaches 7 of 3x. Technically, when I take a limit, I can think of this as pulling the 3 out front and then taking the limit as x approaches 7 of x, and I end up with 3 times 7 or 21. Now here, when we're looking at this particular value, I have to be really careful. If I take the limit as x approaches 7 of this binomial, I might think, oh, I can pull the 3 out front. But the 3 is not common to both the 3 and the 4, so I cannot pull it out front. I'd have to split this up into two pieces and then pull the 3 out front of just the x. So that's the constant multiple law. The next rule that we're going to be looking at is the product law. Now the product law is kind of similar to the sum law. The sum law said the limit of a sum is the sum of the limits. The product law says the limit of a product is the product of the limits. And it's very similar. If I have a limit of a product, I can take the limit of each piece or each part of the product, each factor of the product, and then multiply those values to get my overall solution for the limit. So here I have a product of x cubed and a product of the radical. So I could take the limit of each piece, and then once I find the limit of each piece, multiply them together to get the overall limit. And again, all of these are going to assume that the limits exactly or actually exist. The last rule that we want to look at is called the quotient law. Now the quotient law says the limit of a quotient is the quotient of the limits. So if I have the limit as x approaches a constant of a rational expression where I have some numerator and some denominator, I can just take the limit of the numerator, the limit of the denominator, and then compare those values to get my overall limit. And again, all of these assume that the actual limits for each of these f of x and g of x exist. So for this example, I would take the limit of the numerator, square root of 4 is 2, the limit of the denominator, 16 minus 2 is 14, to get an overall value of 1/7 for my solution. Now for all of these examples, the limit has existed. Let's go ahead and look at some examples to finish this up where we can talk about where we need to be careful to check whether these limits exist. Okay, so for this example, I would like to find the limit as x approaches 0 of 1 over x all over x. Well, this is definitely a quotient, so let's go ahead and use the quotient rule. And if you've had any calculus before, when I say quotient rule, you might think, oh, I'm using the quotient rule as we would a derivative, but that's not what this is. When I talk about limits in the quotient rule or the quotient law, it says the limit of a quotient is the quotient of the limits. So this would look like the limit as x approaches 0 of 1 over x divided by the limit as x approaches 0 of x. Well, the denominator is very easy here. The limit as x approaches 0 of x is 0. I just plug directly in. Here I get 1 over 0. Now you might be tempted to look at this and think, okay, this is really 0 over 1, and I would invert it, and maybe I'd get something to cancel or simplify. But basically what we need to understand is this. This is undefined. This numerator is undefined, therefore the limit does not exist. And because the limit doesn't exist, I can't apply the quotient law. So in other words, I cannot say the overall limit does not exist. So I'm going to have to think of some other way to work with this. So I can look at this algebraically instead. So algebraically, the limit as x approaches 0 of 1 over x all over x. Now algebraically, when we look at this x that's in the denominator is really x over 1. So when you divide by a fraction, when I divide by this fraction right here, I actually multiply by the reciprocal. So the reciprocal of x over 1 is 1 over x. So this is the limit as x approaches 0 of 1 over x squared. Well, we already know, we've looked at this one before. When I plug 0 directly in, I get something that's undefined. And this implies the limit does not exist. So the limit does not exist, and this is the reason why. The reason why the limit does not exist has nothing to do with this up here, because in order to apply the sum law, the constant multiplier law, the multiple law, or the quotient law, the limit has to exist, and I see here that it doesn't. Here we showed the limit does not exist because if we think about this, this graph of 1 over x squared looks like this. And I can see the limit from the right and the limit from the left agree at infinity. So therefore the overall limit is infinity, but an infinite limit is not a limit at all. So therefore the limit doesn't exist. So the best way to work with these is to work a lot of problems. You're going to work a lot of the algebraic problems more than any other. So you're going to be able to find common denominators quickly, work with multiplying by conjugates. And it could be the conjugate of the numerator or the denominator, factoring, canceling, etc. So you have to be pretty hip with your algebra, ready to go with it. Otherwise you're going to run into some troubles here.